صباح الخير. اليوم راح نتكلم عن الايتم ريسبونس ثيوري. الايتم ريسبونس ثيوري راح نشوف بيها a lot of use of mathematical models. So in some sense it's quite sophisticated theory. We'll see here these curves which are called item characteristic curve. Each item is a question. So this is a curve of question. Alright. So this is a curve of the probability variability curve of questions called item characteristic curves. And this big curve is called the test characteristic curve, which is the sum of all these item characteristic curves. So we'll see characteristic curves. All right, a characteristic curve for each item is called item characteristic curve. And the sum of them will be a test characteristic curve. Also, we'll see another kind of curves, which are called the information curves. All right, so this is an item information curve. This is item 1 information, item 2 information. Each question has information curve. The information curve have another, shape. They are different from the test character, the S shape of the test characteristic curve. So you have here the information curve, and this is a test information curve. So we have characteristic curve, item characteristic curve, and test characteristic curve, and we have information curves. And there are item information curve and test information curve. The information curve are important in fact reliability. These are very useful to have reliability from the item response theory, which provides a more detailed of reliability, which is displayed per abilities. So it's a more, explicit form or more rigorous form of reliability, at least more extensive. All right. So now here, this is a very important slide. It speaks about the common ruler concept, which is a very important concept. If you have two exams, all right, and two exams, what we mean by exams is the student responses to these exams. Two exams sit here sat by different set of students and have different sets of items. You see these big items here present. These are called the anchor items, which mean the shared items between the two tests. So this big one is here and it's here. So it's shared between these two tests. But the majority of items in the test are not shared. All right? So if you have two tests, almost disjoint, not disjoint, almost disjointed items, but they might have disjoint set of students, then if both of these tests fit the Rasch model, then we can have a common ruler, common scale that scales item difficulty, and another common scale that scale the student abilities in such a way that in such a manner that we can equate them. So if we equate the items, and we can equate the students also. What we mean by equation, we put the items on a common ruler. This difficulty, the item difficulty, the question difficulty will be displayed on a common ruler so that we can compare their difficulty, which one is more difficult than the other. And here the student abilities also. We can put them on a common ruler and we compare. This student is less able than this student, for example, which is less able than this student. Although those two students are coming from two separate exams. This is something that classical test theory cannot achieve, with any ease. It's difficult for classical test theory to achieve that. While it's achieved if both of our tests come from the Rasch model, they fit the Rasch model. And this is one of the most benefits of the Rasch model, is the common ruler concept. All right. So that's why we always demand, that if we can have our set of question Rasch fit, then it should be. We should try as much as possible to have our exams Rasch fit. So if some questions are bad questions and they preclude the Rasch fitness, then we may delete them in order to make our set of exam as much as we can, as much as possible to be Rasch fit. All right. So this is an important concept. In that sense, a Rasch model is a sort of a prescriptive model and not just a descriptive. We will speak about that later on. So this one should bear that in mind. This is the most important aspect that the Rasch model can do. Now we come to history. Sir Thomas Robert Malthus, he was known to be pessimistic, and he had pessimistic theories like in economy and population growth. He professed that the more we have food production, the food production increased by arithmetic series. Like it increased by one amount this year, one amount, another amount, like the year increased three amounts the third year, and so on. An arithmetic series increased by plus of one plus each year. The population will grow faster. It will grow at a geometric series. At that time, it was called logarithmic series because it's exponential to e, which is the natural number, which is about 2.7. So in the first year, by the end of first year, we will have, like, for example, 2.7 growth. So one growth leads to 2.7 growth. One production, one increase in production of food will increase to 2.7 increase in human growth. Two productions of food will lead to around 7.3 increase in human population till it will reach into a point where this point is called Malthusian catastrophe, where population will override, human production of food. So there will be not enough resources, and that will lead possibly to chaos and mayhem and all of these bad things because population will grow exponentially, and the food production will cannot cope with these growth demands. Malthus have actually, he was an Anglican cleric. I think he was a professor at the West Indian, I am not sure, university or something, a company, and he affected Charles Darwin and Alfred Wallace, and this actually pessimism of Malthus has called actually for a mathematician called Pierre Francois Verhulst. Verhulst challenged actually Malthus and opposed him actually on that thing. He said that the exponential growth is not exponential. At the end, there it will slow as it go up. So there will be like a kind of a roofing effect, a slowing effect. So it will produce the S-shape relationship between, the x-axis and the y-axis. So he called this curve as the logistic curve, and this is the equation for it. So it's not like fx equal e to exponent of x. No, it's like that. This is the equation of it. So he challenged actually Malthus' claims, and he said that the population won't go so fast. But this is the origin of the naming of logistic curves. All right, nobody knows what that name, why he called it logistic curve. The exponential curve he was aware, of them at that time. They used to call it logarithmic curve. So possibly he's opposing to that. He's saying that logistic curve. All right. So now in psychometry, we are using curves now, these logistic curves, in psychometric analysis. All right. So here in psychometric analysis, the x-axis, which is real valued, uh, represent the ability of students in logits. Now, don't care about what does a logit mean. Let's call it a unit on a unit measure on the x-axis, which is the axis that represents the abilities of the students, how much they are able, I mean their cleverness, let's say, and how much they are able in their, I mean, an application, and how much they are competent regarding their knowledge and their skills and these things in the topic they master. It reflects the mastery of the topic they are examined on. So the whole of this curve is about a single question, like for a single item, I mean, like for example, item one in some test. So this is the ability of the students, and the y-axis is the major value is one, and the smallest value is zero, and this represents the probability of correct answer. So, for example, students here, which has zero logit, have around 0.05 probability, like half probability of answering the question correct. So it's like 50-50. So 50% it can answer them correct, the question on, and 50% it doesn't answer the correct. This means what? It means that if I have, for example, 100 students, all of them of ability zero, all of them their ability is zero logits, then 50% of them will answer this question, which is the first question, as we said here. We chose it to be the first question. So 50% will answer correct and 50% will answer wrong. So that's what the curve means. For example, at logit 2, we'll see that the probability of answering the question is 0.881. So about 88% will answer it, and about 12% will answer it wrong. So the probability is higher because the ability is more. At two logit abilities is way higher than zero. So they are more able students. So the probability will increase with the increase of ability, and it will decrease with the decrease of ability. And the relationship is that logistic relationship. As ability go down, 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 approaching infinity, it will approach zero. As ability go up, 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 it will approach, but it will never reach one, and it will never reach zero. So this is the relation of the model. This is C is the guessing, and 1 over 1 plus e to exponential minus to exponent minus a 0 minus b. B is the difficulty. Theta is the ability. B is usually represent the difficulty, and C represent the guessing. And now we can have a lot of really logistic curves. We can have family of logistic curves. This depends on parameters. Parameters here can be understood visually as something that can change, lead to changes in these curves. So for example, the difficulty parameter can displace the curve to the right or displace it to the left. Displacement to the right means that the question is becoming very difficult. For example, students who have ability of 4, which are quite able students, they only have a chance of answering it by 51%, nearly 50%. So this is a very hard, I mean, question. While on the opposite side, if we go like that, this one is called the flooring effect because the majority of students are in the floor, on the floor of the logistic function. While here, sorry, let me put that fixed. I won't change the discrimination. While here like that, it will be easy because we decreased the difficulty B. So it will be easy. You will see a roofing effect. Like a student at -4, which is quite low ability, still he can answer the question by 0.87. 87% has chances to answer this question. So this is pretty much easy. Of course, you are only seeing the roof of the function here. You are not seeing the whole function. The whole function is beyond that. It have the same shape, but beyond this scope. We only see this part because our students are here. Are also here, you only see this part because we displaced it, we pushed it to the left. But here, while we are pushing it like that, we fixed discrimination at 1 and we fixed guessing at 0. This is called one parameter because these functions are only changing according to one parameter. So the family of all such curves that are changing only by that parameter of difficulty is called the Rasch model. So the Rasch model is a family, is a set of curves. A set of curves which is common between them, they have the same discrimination of 1 and the guess factor of 0, guessing of 0. But in reality, we can have a lot of families of Rasch model because what is important is that they should have a fixed discrimination and fixed guessing factor. So if we fix the discrimination to all 1.7, this would be another family, and those will change only by difficulty. And their guessing is also 0. So this is another family of Rasch model, another Rasch model. So, but the majority, I think, of Rasch model is they fix the discrimination at 0. Okay. So the three parameter logistic, it changes by by guessing, and also the slope can change like this. Look how the slope can change, and guessing also here will change on this type. This one you see, and it can change, of course, by difficulty. So a three parameter logistic is the group of family of the curves that can change by all of these factors. So it's a more flexible family of curves. It's not as rigid as the Rasch model, which fix the discrimination and the guessing into 1 and 0 respectively. Uh, so this is as much as that for curves, right? And for the logistic curves. The gold standard, we can say in some sense that the Rasch model is the most frequently used, and it's considered to be like a kind of a gold standard and a requirement for making an excellent measurement. While the other curve, the three parameter, the models like this, two parameter logistic model and the three parameter logistic model, are usually considered descriptive. And then they try to fit the model to the data, to the test, to get a good description of what is the student responses. But they are in that way they will be model specific, the responses, while in some sense a Rasch model seem to be more objective. We'll discuss that later. So now we'll go to the Rasch model. So as we said, the Rasch model only change by difficulty parameter, and this is the equation of the right of the Rasch model is that the probability of theta equal when 1, which is the probability of the students of that ability theta to get the answer correct is equal. Sorry, the probability of theta. Yes, it's the probability of getting the answer correct by these students is 1 over 1 plus the exponent of which is e raised to the exponent of minus theta minus b. So it is theta minus b that determines the probability. Of course, here we are having three items. Item 1, you see, this is item 1b, which means the difficulty of it. Let me fix it here. It is difficulty at 2. 2. What do we mean by that? By difficulty of 1.8. Let's increase it to 2. Let's see. This is the difficulty of 2. How do you know the difficulty of an item? Of course, as I said, every curve of those represents one item. So we come here, we see where is zero point 0.5, which is 0.5 chance of answering a question. We see the point on that curve that correspond whose y-axis is zero point 0.5, which is here. And then we take the x-axis of this point, which is -2. So this curve will have -2 difficulty. It means that we need students of ability -2 to answer it by 50% chance of getting it answered correctly. While here you see it is 0, and here you see it's 1. The more the difficulty increase, of course, this means that the question is more difficult than the other. So as we said, that Rasch model is, we try to make as much as possible our exams fit the Rasch model. So this is the gold standard in some sense. Okay, so we go now from there into what is the underpinning of Rasch model. I mean, why Rasch model is very important like that, that it has almost a prescriptive philosophy. It's prescribed as a gold standard that our questions must, or we try to fix our question to abide by it, to fit it. We may delete some questions, we may revise some questions in order to make them fit the Rasch model, as long as they don't affect validity and reliability and other measures. And especially as long as they don't, the removal of these questions don't affect validity, then they will be recommended to be removed. I mean, in order to fit the Rasch model. Although just fitting the Rasch model is not often the cause. Most of these questions that do not fit the Rasch model will show some pathology most of the time. So we delete them for that also. So no, the Rasch model, let's take an analogy of the Rasch model. The idea of the Rasch model is that the outcome of something, like here, there is a chance this man wants to elevate, he's a heavyweight lifter, so he wants to elevate the barbell. Now, what are the chances of he succeeding? The chance of success in elevating the barbell? The chances clearly will depend on two things: on the person's ability, which is here, the lifter's strength, let's say, and on the weight of the barbell, which is something which is similar like to item difficulty. So the more the barbell has a weight, the less is the chances of him lifting that barbell. It's like the more difficult is an answer. And if we fix an ability, for the more difficult is an answer for that ability group, the more difficult for them to answer, the less is the probability that they will answer that question. I mean, on the other hand, if we have the same questions, but we have another group who is more able, has higher ability than them, then the chances of answering these questions will increase. But the ability of the group is fixed. The ability never change unless the person are changing. The item difficulty never change unless the item is changing. So each item, like a barbell here, has fixed difficulty. Like here, this barbell has a fixed weight. All right, is not affected by the person who lifted it. Unless we change the weight, that will change the barbell. I mean, remove some rings, then it will change the weight. So here, if the weight of the barbell is at the same strength, let's say, as same magnitude as the lifter's strength, both of them are equal. So they'll have 50-50% chance. He will have 50-50% chance of elevating it, of lifting it. All right. Well, let's see like that. We see something like here. This principle. Let's fix the man the same ability and increase the difficulty. And like let's increase it now like this. This is the probability counter. So increase the difficulty, probability will become low. You decrease the difficulty of the item for the same ability. He will smile, be smiling, and he will get a good chances of elevating it. So that's clear, really. And if we fix the bubble, but we increase the ability, we'll have higher chances. If we decrease it, have lower chances. So actually, it's the difference between theta, which is the ability of the person, minus b, which is the difficulty here in logics. This is the thing that is affecting the probability. The probability is directly proportional to theta and inversely proportional to beta. You see, there is no discrimination changes. We are not, for example, elevating the bubble when they are tilted, for example. We always put it in a horizontal level. We don't change its tilt because that would affect it if we allow it in the game. We don't change also, for example, its primary distance from the floor. It's like the guessing. We don't change all are on the floor, put on the floor at the same distance at the beginning, and they are not tilted. They have the same 180-degree angle, and they are parallel to the Earth. So they have like fixed discrimination and fixed. I mean, no chances, no. I mean, increasing its chance, like let it lift it from a higher position. All of these fixed. The only thing that affects the chances is his ability and difficulty. This is the difference between his ability and difficulty that is doing it. Okay, so that's clear. From this thing comes the principle of the Rasch. I mean, the idea of the Rasch. What the Rasch will do is that it will make an assignment to the test item's difficulties. For each item, it will give it a number. And this number that serves a measure that serves to measure its difficulty, the magnitude of its difficulty. And it will give each person in the exam a number which serves to measure his ability or her ability. And this is fixed per person. And also the number which is given to the item is fixed per the item. All right? It's not affected by the person who tried to solve the item, whether his ability is high or not. What will be affected is the chances of solving the question, but not the difficulty of the question and not the ability of the item, much as the weight of a barbell is not affected, is not changed by who. For example, here the weight is fixed. Look, here the weight is fixed, but we change the ability, but the weight is fixed. Or here we change the difficulty, but the ability is fixed, changing the difficulty. One change, changing the heaviness, I mean, of the one change the ability will remain fixed. Even though the probability of success is changing, but the ability isn't the same. And when we change the ability for the same barbell, we change the people, the barbell is still having the same difficulty. So there is a kind of a dependence between difficulty and ability. So what are the assumptions of the Rasch model? What does the Rasch model assume? The first assumption is unidimensionality. So unidimensionality. There are some assumptions for Rasch which are very important assumptions. So if we want our exam to be Rasch fit, we need to design it in a way that doesn't disturb these assumptions. The first assumption is unidimensionality. The test items must measure one latent trait. So the test as a whole must measure one latent trait. Multidimensionality can be introduced if one make it, make the exam questions in such a manner that they may examine more than one talent. For example, if one introduce a question in a very high kind or high kind of English or a high profile language that only minority or only some of students can master. And then the test become a test of that kind of language in addition to what is supposed to test. For example, I want to make a test in neurology, for example, for fifth year medical students, for example, in Iraqi patients. So the medical language, language of medical colleges in Iraq is English. But however, Iraqis are not all of them master English very well. So if I introduce the case scenarios, which is usually case scenarios questions, in a kind of high level English, very high level English, then the test won't be only just examining their application of neurological principles. It will also be a test of their language. It will introduce language as a dimension and as another dimension. And so this will break the Rasch fitness, because Rasch is only measures one latent trait, and that's it. So introducing multiple traits will cause non-fitness to the Rasch model. This thing also sometimes might be caused by, for example, logicalizing the test too much. So you introduce the test in a very high logical language, like all of these following are false, except, and then within the option also you say all of the following or the above are false, except, and all of these like logical circles. So if you make most questions in that genre, then this will introduce the ability to deal with logical thinking, complex logical thought, as another trait besides the content of the questions, which are supposed, for example, to be neurology, about neurology. So we'll introduce another dimension. So in order to avoid that, questions must be written in language appropriate to the students, and simple, clear language without any, not confusing, and it doesn't require very high level language. I mean, it's suitable for most of students. Shouldn't introduce like logicality or some kinds of tricks uh, like those present in IQ questionnaire. It will be a question about IQ, not only the subject matter. Also, sometimes some question might have differential item functioning, so females can master it or males can master it better than the other gender, and so this will also introduce dimensionality into the question, multiple dimensionality. One of the biggest problems with unidimensionality, especially in some medical modules, is that the medical modules is made of multiple, disciplines. Like a neurosciences module incorporates various disciplines that are not, they don't apply. The method of thinking in these disciplines might not be the same. For example, a module which have neurosciences, a module which has neuromedicine and neurosurgery, and for example, neuropharmacology. So the principles of these disciplines are not exactly the same. So this might introduce dimensionality, also multiple dimensionality, because students might differ in the proportion of mastery of these disciplines. However, if one introduces the questions, write the questions in an integrative manner or integrated manner, in which each questions has some of these disciplines, then you will be testing their integrated ability, or the ability to integrate knowledge in that module, and this will be one, and it will be a single trait. So this highlights really the importance of trying to reduce multidimensionality if you have a module or an exam of a module which has multiple disciplines in it. Uh, so this is about unidimensionality, which is very important. I mean, and one should take care when he or she designs the exams items, that at the end the exam, the whole exam shouldn't, test different traits. It should test only one related trait, which is the subject matter of the exam itself, which is what the exam is primarily designed to, according to the curriculum, of course. The second assumption, which is very important, is local independence. For your questions to fit Rasch model, these questions must be independent in the sense that the answer to one question doesn't give you a hint to answering another question. So the probability of answering a question or probability of answering the items must be independent, totally independent. So one must not uh, make serial questions, like a question which asks about the diagnosis, another question which asks about the treatment, and a third question which asks about the prognosis, all of a single stem question, or all of them have exactly the same stem, but they ask about different aspects of that condition. Those will be linked questions, because once you know the diagnosis, you can go and know the treatment, and you can go and know the prognosis. And the opposite is true. I mean, if you get the diagnosis wrong, so you might get the treatment wrong, and you might get the prognosis wrong. So they are linked questions. The answer to one question of them will affect answering the other questions. Also, sometimes redundancy in test items. Redundancy means that you add items that are virtually the same. Whether they are the same verbatim, they are copied verbatim, which shouldn't be, or whether they are, not verbatim copying, but they are phrasing exactly of the same, paraphrasing of the same questions. So you have two or three questions that are basically the same. So this is called test redundancy, because these other questions, like two or three questions, there are no need for them. The test will be predictable. So predictable because the same answer is to all questions, because they are virtually the same questions. All right. So this shouldn't be allowed, and one must not design questions with the aim of answering them in a dependent manner, like answering one of them leads to the answering the other one, and like that. They should be completely independent. Breaking of local dependence or local independence will cause violation of Rasch model. And now monotonicity. Monotonicity means the most able will do better. So the higher is the ability of student in an exam, the higher is the probability of getting the answers true. So when you design an answer, when you design a question, an item, you should design it with some difficulty level in such a manner that it differentiates between the highly able students and the students with low ability. So the more able student should have more probability of answering it than the lower ability students. So one must not design a question that is very hard, that all students will use guessing to answer it, and by then it won't differentiate. The ability of students will be irrelevant. Or on the opposite side, write a very simple, very easy question that all of the students will answer it. And in this way, it won't discriminate higher ability from lower ability students. So it will break monotonicity assumption. So in order to do that, the student must be tailored to the difficulty. So the questions must be tailored to the difficulty level of the students present in the cohort. So that's the assumption of monotonicity. Now we come to the fourth of the assumptions of the Rasch model, which is specific objectivity. And this states that comparisons are irrelevant across persons and items. What that means actually is that item on item must be assigned a difficulty that shouldn't be affected by the persons answering that item, by the ability of them, I mean, shouldn't be affected by it. And also, on the other hand, the persons should be assigned difficulties, should be assigned abilities. The person abilities assignment must not be affected by which item, by the difficulty of the items they took in a test. So we have two kinds of invariance. First is called item invariance. And as I said, an item invariance means the item will have a fixed difficulty. So when the Rasch model assigns difficulties to items of the test, it will give each item a fixed difficulty, a single value. This value will not change, despite the students, which students answered that question at all. Even these items, if they are used in another test, and that other test is also fitting the Rasch model, then we can equate these items in such a manner that they will have exactly the same value on both tests. So an item shouldn't change in difficulty according to the cohort of the students who were answering that. To see this analogy, we see it here. You see this student, sorry, it's not a student, this guy in red, he's a muscular guy, so he has more ability to lift the weight, I mean the barbell. The other one is thin, so he have less, this symbolize less activity, less ability, less ability. But both of them are lifting exactly the same barbell. The weight of the barbell will not be affected, it's fixed. It has two rings, let's say each ring is 10 kilograms, so it's about 20 kilograms, it's fixed. Whether it is lifted by this person who is muscular and have high ability to lift it and manage to lift it, or whether it's lifted by, I mean, this one, the thin one who has less ability, he couldn't manage, or he lifted with great difficulty, but still it's the same weight. So here, if the weight signifies, I mean, symbolize the difficulty of the item, you see it will be assigned the same weight despite who is taking that item. That's what it means. So this is called objectivity. I mean, there's a kind of objectivity to the estimation of item difficulty. It will be given one number. Each item will be given number. Its difficulty won't change unless the item itself will change. It will be revised or modified. Then it might change in difficulty. But as long as it remains exactly how it's stated, then its difficulty will be fixed. And after equating them with another exams that fit the right model, it will be fixed, no matter what the cohort of students taking it. It's a fixed difficulty, one difficulty for each item. So this is what's called specific objectivity. Also persons, let's take the other example here. A person, when we assign by the Rasch model, when it assigns a difficulty to that person, when it's assigned ability to that person, it says that this person have such and such logics of ability. This will be fixed per person. It won't change. Even if he takes a different set of exams, even if he answers along different items in the test, still the ability is fixed. It's one number, a single number. Each person have a fixed ability, each person. So it's like here, this guy in red, he's the same person here, and here he's the same one. So since he's the same person, he has the same muscle bulk and the same muscle power, which means the same ability. But here he lifted a very light barbell, only two rings on each side, while here they are big and heavier rings and three rings on each side. So this is a heavy barbell, so he couldn't lift it. But that doesn't mean that his ability decreased. No, it's exactly he has the same ability here. The ability didn't change. What is changing in all of these situations here in this example is the probability of lifting the barbell is changing according to difficulty and ability. Yes, according to heaviness here, not difficulty, according to the heaviness of the barbell and the muscle bulk of the person, which reflects what's happening with, for example, as an analogy, it reflects what's happening in questions. For in questions, what will change between questions is the probability of answering the question will change. But the probability of answering the question is not the difficulty of the question, and it is not the ability of the person. Abilities and difficulties are something discriminant, something different from probability of answering questions. So, the difficulty of answering questions, the odds of answering questions, the log odds of answering questions, all of these are different aspects that describes the chances of answering questions, the probability of answering it. And the probability of answering question is different from the difficulty assigned to questions. I mean, the difficulty of the items, and it's a difficult thing. It's a different thing from the abilities of the person. They are not the same. Person's ability, the item's difficulty, and the probability of answering questions are all three different entities, and they shouldn't be confused by each other. What does that mean? What it means here is that if we have a test and that test was found to be fit to the Rasch model, then this means that this test have had or have achieved or met the underlying assumptions of the Rasch model. So all items in the test measure one latent trait. There is a local independence, and there's monotonicity, and there is a specific objectivity, which means that the item's difficulty is invariant across abilities, and and the person ability is invariant across item difficulties. So there is item and person invariance. So if we achieve that, then this means that the assignments that the Rasch model does to the assignments of difficulty and abilities that the Rasch model gives to our test items and to our students are objective. They can be used and compared across other tests if these other tests also fit the Rasch model. And this enables us to have the common ruler of difficulty and the common ruler of ability that we spoke about in the earlier slides. So that's pretty much the benefit of the Rasch model, is the comparability across tests. Now we come to a very important subject, which is the logit. What is the logit? What is a single logit? What is the logit unit? The logit is basically, as we spoke before, is the unit on the x-axis of a logistic curve. That's it. That's the logic. It's a single unit. One logit is a single unit on the x-axis of a logistic curve. But We are interesting to mean what does that mean exactly? How we are to understand that unit. The major thought about it is we understand it in terms of how it affects uh, change in the the odds of solving the question. Correct. So, for example, we are speaking about, for example, logics of abilities of students. So we say, for example, that student A has ability of two logits and student B have ability of one logit. So they have a difference of one logit between them. Student A is higher by one logit than student B. So what does that mean? I mean, being higher one logit of ability. If we look at here in this example, on the left we have the logit difference, which is here spelled between difference between theta, which is the ability, minus the difficulty B. All right. But nevertheless, let's take the absolute the value of that difference. So let's see when they are zero, when the ability is equal to the difficulty, you have an equal chance of answering the question. Equal chance of answering the question. So this is called one-to-one odds. Odds. The odds are one-to-one because they have equal chance of answering. It's 50% probability of answering it and 50% probability of getting it wrong. The odds means p over, I mean divided by 1 minus p. P is the probability of answering the question correct. 1 minus p is the probability of answering the question wrongly. So this is the odds. So it's better to think about probability in terms of odds, I mean, and how odds compare. This is better. So if you have the ability, for example, in the question that we spoke above, the situation, I mean, when we have a student who is one logit ability and another student who is two logit ability. So let's say that they are trying to answering a question whose difficulty is zero logits. The difficulty of the question is zero logits. So now, the first student, which has one logit ability, will answer that question by, which is plus one, here plus one. It will have plus one, the difference from the difficulty. This plus one logit increase will cause an increase in the odd ratio by a multiplication of E, the natural number E, which is 2.7, approximately 2.718. So the odds ratio will increase from before it was 1 to 1 at zero level logit, which is which was in this case, it was the difficulty of the item, it was zero. So it was 1 to 1 logit, sorry, 1 to 1 balance, let's say. And if we increase it, it will be 2.7 to 1. So the student with one logit have higher chances, higher odds than the student with zero logits. And the height is the multiplication by E. Let's see, the student with logit 2. Logit 2 will cause an increment in odds, which is success over failure, of 7.3. So it jumped from 2.7 to 7.3. So when you are at two logits different distance from another student, it means your odds, your chances of answering the question over your chances of failure increase into 7 times that of the students below you by two logits. That's what it means. So it's a high increment. So let's take three logit difference. Three logit difference means that the odds will become 20 times more than the odds of one before you by three logits, lower than you by three logits. So actually, the logit increase, if you increase by 1 unit, the probability, the odds will increase exponentially. It will increase by a multiplication of E, the natural number, which is 2.7. It reminds us of the first question, the first slide about Malthus, when we saw that food production increased by arithmetic series, like by addition of ones, and how the growth of population was increasing exponentially. The same thing you see it here, exactly the same thing. As the logit increase by addition 1 unit, at each unit of addition to the logit scale, going more, I mean, at each unit, the odds will increase by a fixed amount, which is by a multiple of 2.7, 2.72, which is the natural number, E. So it's a great multiple. So it's nearly 3 times or more than the one which has one logit lower. Being more, 2 logits more, it's about 7.3. Be 3 logits more is about 20 times you are having odds, more odds than the one below you by 3 times. If you go 4 logits, look at 4 logits, huge. You'll have 54.5, about 55 to 1 odds. This is the balance, 55 to 1. So it's 55 times more than one who is lower than you by 4 logits. So the logits make exponential, growths in the odds, in the curve of the odds. If you see that, this curve, the blue one, is the odds curve. This is not the probability. This is not the ace shape. This is not the logistic curve of Verholtz. This is actually the exponential curve. Logits, which is here defined as P over 1 over P. This is the odds. Odds divided defined as P over 1 over P. P is the probability as success. As we say, it's the ratio that compares success to failure. This odds here is displayed instead of probability. So this is the plot of the odds against the ability in logits, not of the probability against the ability. This curve is exponential, not logistic. So let's see here. If you have 0 logit, you will have a chance of 1 only. You'll have chance of 1, which is 1 to 1 odds, which is that's what they say sometimes 50-50 chance of answering the question. The same, 1 to 1. See here, 0 and 1. If you go to 1 logit, it will increase by 2.7. If you go up to 2 logits, it will increase by 7.2. If you go up 3 logits, it will increase 20. If you go 4 logits, it will increase up to about 54 times. So quite a lot. If you go down now, if you go from 0, if you go down, you will decrease by 0.37. You will decrease about to the third, about to 1/3. And if you go down, you will increase to 1/9 of the logits from the 0. So each logit unit decrement will almost decrease the odds by 1/3, about 1/3. So it's a lot. Here it will become 1 over 20. Here it will be 1 over 55. So it's exponential. Now, if we take the logarithm of that curve, the log odds, the logarithm of the odds, and we plot it against the x-axis, we will have that. This is still we will have this curve. We will have a line, because this is the log odds. Here, this is the log odds. You see here in this y-axis, you are seeing the odds here. 1 to 1, 2.7 to 1 here. This is 7.3 to 1, it means. Everything 20 to 1, 55 to 1. These are odds here. You are seeing the odds. And this is on the right side of this x-axis. You are seeing here the logits. You are seeing the log odds. The logits, the logarithm of the odds. So the logarithm of E1 is 1, of course. The logarithm of E to the exponent of 2 is 2, and this is 3. You will see that this will match the x-axis exactly. So actually, the x-axis unit is the log, the log odds, the logarithm of the odds, the logarithm of the chances to get to answer the question correct over the chances of not answering it correct. This is the log odds. So you see, that's each log is how much it will cause a jump. Here it will go here from, this is one logit, let's go one logit 2.7. Another from one, why is not going here? Okay, another from 2 to 3, it will be about 20 from the beginning. But it will increase it from 7.3 to 2. Every increment is by E, a multiple by E. Every one logit increase the one before it, the odds before it, the odds of success by about E, by a multiple of E. So an incremental logic, the logit ability leads to multiplication of ability by E. A decrement in logit of ability leads to decrement of, the odds, sorry, the odds rate, not the logit, the odds rate by E. So you understand the logit from their effects on the odds rate, okay? They are actually the logarithm of the odds. The logits are nothing but the logarithm of the odds. Okay, so back to understanding the logits. So we said that one logit ability increase will lead to an increase in the odds. So an odds increase by a multiple of E. That's what it means. So what it has, if it, what it means if it decreases. For example, if -1, let's take for example -1. What happens is that the odds of failure will increase by 2.7, and the odds of success will decrease to about the third. It will be 1 over E. If it's -2, it will be 1 over E to 2, which means 1 over 7.3. That's the success that it will be. 1 to 7.3, 1, 2, 3, 4, 7, 9.3. That's what it be. This is the odd of success. So it will be very, if we take it in terms of odd, and we want the failure to be always 1, so it will be 0.135, which means over 1 over 7.3. This is 0.135. So it's about 1/7. It will decrease to 1/7. If it's -2, it will be to decrease to 1/20th to 1. So it will decrease a lot. So that's what it means. Now, what it means to say that the difficulty is, for example, 2 logits, not the odds, the difficulty of that question is 2 logits. What that mean actually? It means that it requires an ability of 2 logits to get the question one-to-one difficulty. 1-to-one odds. But we know that. But what it means to say that there is an increment in the difficulty by 1 logit. For example, we have 2 questions. The first question is, for example, 2 logits difficulty. The third question is, the other question, sorry, is 3 logits difficulty. So the other question is higher in difficulty than the first question by +1 logit. So what does that mean? How it affects the odds of answering that question? It affects it negatively. It affects it negatively. What will happen is that the odds of answering that question for the same ability students, of course, for the same ability students, for the same ability group, it will decrease, the odds will decrease to about 1 over E. So it will lead to decrement in the chances of answering this question as compared to the chances of failing this question. Okay, so it will lead to decrement. And of course, if the difficulty increase by 2 odds, also the chances will drop into about 1/7 to 1. the odds ratio will, I call it also as odd ratio. It's the same as they call the odds. The odds will decrease into 1 over e to the exponent 2, which is about 1 point, so 1 over 7.3 or something like that. If it's 3 logits more difficult, it will decrease to about 1 over 20 to 1. Decrease, a lot of decrease, I mean, very great decrement. So to see it here, I mean, sorry, not here. So if a question, let's say difficulty was here, and it increased in difficulty like this, so the odds will decrease actually. This is not the ability, this what you are seeing is the ability versus the odds. One should make another curve, which is the difficulty versus the odds. You will see it, the curve is the opposite of that curve. So both the ability units and the difficulty units are the odds. It's the same unit. Sorry, the logits, sorry. The logits. And we said that the logit unit is actually the logarithm of the odds. Now, to understand that a little bit, let's take this whiteboard and see. What we need to understand, there are probabilities of answering the question. For example, if we have a question, let's say item 3, which is the third question in the set. This item has a probability of answering it, which is P, all right? PI3, which is the probability of answering I3 by, let's say, a certain ability. I won't go to the ability, I will fix some ability. Let's say the probability of answering it is 0.75. So it is 57 percent, 75%, sorry. What does that mean? In the odds are another way of displaying the probability as a leverage. So it would be 0.7% over 0.25. This is the probability of failure, 0.25, and this is the probability. So it will be about 3 to 1. This is usually expressed as 3 to 1. This is the odds. All right? This is the odds. 3 to 1. So now we always speak about the odds. So now the logit, for example, the logit of a certain probability P is actually the natural logarithm of the odds. The odds is P over 1 minus P. That's what it is. So for example, the logit of this probability, which was 0.75, it is the natural logarithm of 3. All right? So something like this. So this is the logit. The logit is the logarithm of the odds. So the logit of a certain probability is the logarithm of the odds. Let's erase that. Okay. So suppose we have a person now. We will speak about ability. It's theta j. This is the jth person in the set. So the theta, which is the ability of the person j, let's say it was 2, 2 logits, 2 logits, 2 logits. All right. Let's say another person, theta, for example, let's call him k. Theta k, let's say it equals 4 logits. Now, suppose, for a certain, we're speaking about a fixed item I. Suppose that these two logits for this question I produced odds that were 2 to 1, and the odds equal 2 to 1. So the probability of answering the question is double the probability of failing it. All right. What would be the probability of answering that question, the same question I, by the person K, which has the ability level theta K? The ability level is 4 logits here. So it increased by 2. What that will be? This will be 2 multiplied by the difference in ability level, which is 4 minus 2. Hmm? All right. E, like this. That's how it will be. All right. Let me write it well. This is not written well. Multiplied by E is 4 minus 2. Because it reads by 2 logits, each logit will add a multiple of E. So it will be like 2 multiplied by E to the exponent 2. That's what it will be. And it will be like 2 multiplied by 7 something point 3 or something like that. That would be his odds. Okay? Of course, to 1. This is to 1. That would be here, his odds, because the original odds was 2. So we multiply it by E to the difference in exponents between these exponents. That's how we know how much it will be. So it will increase. So the first one, which has an odd ratio of 2 to 1, the one which is at 4 logits, 2 logits ahead of him, will drop to an odd ratio about 7 point, which will, it's about 14.6, right? 14.6 to 1. That would be the odds of solving the question by. So the odds of success, it has 14.6 times more probability of success as compared to the probability of failure. I mean, the probability of success is 14.6 times more the probability of failure. So it's quite huge, from 2 to 14. Just two logits. Just two logits on the logit scale, from 2 to 4. Increase the odds from 2 to 14. A lot of increase in odds. And you can imagine something similar to that, but on a difficulty of question. If a difficulty of question rise by 2 logits, but here it will be the opposite. It will be a decremental side. It will decrease in the probability of answering the question. So what we are having actually is that both difficulty and ability, both of them are expressed in terms of logit, and that means the logit means how much the odds of success. So both of them are expressed in terms of the logarithm of the odds of success, which is the log odds unit, which is the logit. Actually, logit means nothing but logistic unit. That's what logic means. Logistic unit. This is the IT, and this is the log. So it will be log it, or logit. It means logistic unit. That's it. So both the difficulty and the ability have a unified unit system. It means multiples by E. Multiples by E. That's it. Two logits increase mean increase by E to 2. Three logit increase means increase by E to the exponent 3. Two logit decrease means a decrease in the odds by E to minus 2, which means 1 over E exponent 2. Three logit decrease mean decreasing by E is minus 3, which means multiplication by 1 over E is 3, or the actual division by simply division by E to 3. So that's what it means. That's it. It's as simple as such. So the Rogers unit is simple. It's just a conversion from an arithmetic scale to an exponential scale on the odds, not on the probability, on the odds. And that's all. So I hope that this explains the logic and how one can quantify the logic. All the quantification are in terms of how it affects the odds of success, which is the ratio of the probability of success to the probability of failure. How much success have chances more? How much more multiple than the chances of failure? Okay, so that's it. It's just the logarithm of that, and that's all about the logics. If you understand the logics, if you handle the logics, then you are getting your hand. You are gripping the Rasch model by your hand. Okay, so now, as I said before, we come to a very important concept, which is the concept of fitness or fitting to the Rasch model. Now, when we have a test and the test is completed and we are going to do psychometry, we have the student responses. We have what is called the student item response, which records the responses of the student on each student on each item. And we are having an MCQ exam, which is dichotomous marking. Either he has 1 if he gets the question right, or 0 if he gets the question wrong. So anyhow, we have all these 1-0 matrix across all items and students. When we feed it to the Rasch software, the Rasch at the end will give us estimates. It will give us measures. It will assign to each item a difficulty, a number, a difficulty in logics, and it will assign to each person who took the exam an ability in logics. Each person have one ability. Each item has one difficulty. Now these items, this vector, hmm, this vector of difficulties, and this vector of all abilities per students and the first per questions, of course. These vectors, these are the nearest values, the nearest probable values that a Rasch curve can be to this set of data. And this is what we call the expected Rasch model or the expected Rasch curve. This is the nearest one among all Rasch curves. It's the nearest one to that set of data. However, the nearest Rasch curve doesn't mean that the set of data is fitting to the Rasch curve. What does it mean to say that our data or our responses, or whatever we call it, the test, that our test is fitting to the Rasch data or to the Rasch model? What does it mean easily is that our students, the student who have ability, which is assigned to it by the Rasch itself, by the Rasch model, students of a ability group, say one logit, all these students, if the Rasch model says that the expected Rasch nearest to that group is, for example, it will have half probability, or let's say one third probability of solving that question. This means that the observed, look at me, the observed probability, which is the proportion of these all of these students which will solve this question right, will be exactly also one third. That's what it means when we say fit, Rasch fit. This is an ideal case of Rasch fitness. Of course, you don't see it in in practice. What we see in practice is that the observed percent correct per student on that item is within what is called Bernoulli probability or something like that. It's within variation that is permissible by chance. It's not far away from the expected value by the Rasch model. It might be different from it, but that differing is due to noise, due to the randomness, which is due to calculating these things, because these calculation depends on chance, all of them. So whatever it is, that's what fitness means. Fitness means that the observed percent correct of the ability students uh, matches what is expected, matches the expected probability of Rasch. This is ideal, or at least at the distance that is permissible by chance or by luck. So that's what it means. So suppose now we fed our Rasch software with this student response curve, which is a 0 1, sorry, student response matrix, which is a 0 1 matrix across all students and items. And the Rasch software assigned each student an ability and each item a difficulty, and of course from that it can compute the the Rasch curve, which is the item characteristic curve. It will compute it because it has the difficulty of the item and has all the abilities of the student. So it will can plot the Rasch curve from the formula, from the Rasch formula, which is that p theta equal 1 over 1 plus exponential minus theta minus b. So according to that formula, it will compute this nice red line. This means that this line is the nearest of all Rasch curve to this model, to this expected matrix of responses. What it doesn't mean that this nearest Rasch curve is fit to our observed data. It means it's the nearest to it, but it doesn't mean that it is fit. In order to know it is fit or not, we need to check it. So what we do, first, we divide all of our students into bins. So we say that student, for example, from -3 to -4, all of them, we put them in one bin. From -3 to -2 in one bin, like that. We put them into bins. Now, the second thing is that we will take the average ability of each bin. You see these circles in red, the red circles inside the bins. These are the average. This is the average ability, which means that the sum of ability of all student in that bin over the number of student in that bin. So it will have the average ability. So each average ability will represent the ability of that bin as if all students in that bin have that ability. Now, after that, we will calculate the number of students who got that item correct. Don't forget, all of this item is about one question. Let's say question number one. So how many students in each ability group got answered question number one correct? This is the observed. This is the observed proportion correct. The observed probability of answering the question. And now we put that here. We put each one of these that we calculated here on the y-axis, because the y-axis is the y-axis of the probability. Now these blue dots are observed probability. These are not expected. The expected probabilities are here along that Rasch line or Rasch curve. But here, these are the observed. Now we match each observed with the average, with this average of each ability group. So we do that, and then we match. Now here we will have a curve, and now we'll see the distance of each one of these spots from the expected. So for example, let's take that spot. This spot is the average of this group. So we put a perpendicular line and see where how much it is. There is a difference, but not a much difference. This one is opting on the curve. This is near the curve. This is near the curve. All of them are near to the curve. So they are fitting into the curve. So the expected values, the expected, success rate, the expected probability of correct answer almost matches the Rasch expectation. So this model is fit. It won't be fit if these are very far away from the Rasch model. All right. So this is the fitness. This is how we assess the fitness. However, there are certain parameters to assess that fitness. And we have also types of fitness or misfitness. So how we do that? Let's see that. This is the same. This is the Rasch expected curve for our item. And the red dots are the observed probabilities for each ability group. Now, what you see now is a good Rasch fit. Most of them are fit to the Rasch model. They are not overfit. They are not on the Rasch model, and they are not away from it. So they have good Rasch fit. So now we see, what does it mean to say that there is overfitting of the observed responses to the Rasch model? Overfitting, which is not an expected fitting to the Rasch model. It's more than expected. So this is called overfitting. It will look like that. All dots will be exactly on the Rasch model. This is not expected because there should be some randomness due to noise. So if you see it like that, this means that our set of questions is very predictable. So this is the first thing, overfitting. Next, we'll go to underfitting. So overfitting means all of our, or let's say the observed values are unexpectedly close to the Rasch curve. Now, underfitting is the opposite. This is underfitting. This is the opposite. Underfitting, that they are unexpectedly away from it, like this. This is underfitting, like this. This is even more underfit. So it's away from it. Every one of those dots is away from the Rasch. Okay, so this is underfitting. Look at the vertical distance between a dot, which is the expected value, and between which is the observed value, this one, and this one, and there is a big difference here. So this is now this is we come back to Rasch. These are Rasch fitting, and this area of the curve is divided into two. The area in the middle, right? The area of the middle in the middle. This area in the middle is called the infit area. Okay, the infit area. The area in the middle is the infit area, but the area at the periphery, the area in the middle is the area near the difficulty of question. We said the difficulty of question is where we have the point which is zero point 0.5 probability, and this is where the curve intersects. So this is the difficulty, the area of difficulty. The area around the difficulty of question, this area around the difficulty level of question is called the infit area. While these areas here in the periphery, the roof area and the floor area, are considered as the outfit area. So now we can have both kinds of misfit. We can have an overfit or an underfit in the infit area or in the outfit area. Okay? So for example, if we go to the infit area, let's say that this is Rasch fit. Let's say what is infit? Infit overfit is this. The middle area will be overfit, but the peripheries are not overfit. The opposite is the outfit. Now this is Rasch fit. What would be the outfit overfit? This would be the outfit overfit. So the periphery will be overfit, but the area in the middle is just Rasch fit. Now let's go back to Rasch fitting. Let's say what is an outfit? Actually, sorry, infit, underfit. So the infit area should have the observed values, these red dots, away from it. Yes, that's it. Look, the area in the middle, which is the infit area, has an underfit. There is an underfit infit, and there is sometimes outfit underfit. This is the outfit, which the peripheries are outfitting. Each kind of these indicates something. Each kind of these indicates something. So the outfit and the underfit, these are actually usually calculated by different formulas. Usually the outfit is the average of the standardized residuals. So it's affected, this average is affected by the outliers. So that's why it's affected by the periphery, the outfit. While the infit is different. The infit is a weighted form, a weight form of an average, in which the variance is, is multiplied by the square, the squares of, it's the sum of the variance multiplied by the squares of the residuals over the sum of the variances. So this one will not be affected by the outliers. So it will be only affected if it's in the infit area. Of course, if the infit area has an underfit, this is one of the worst things because the infit area is the target area of the question, because this is the steep area of the Rasch model. It's where it's more discriminative, and the people around this area, they are the people around the difficulty level of matching the difficulty level of that question. So this question is meant to them, it's targeting them. So this means that the people with the abilities targeted by this question are showing misfit, which is underfit, which reflects a bad design in the construct of questions themselves. There is a problem in the construct itself of the questions. While the outfit is usually affected by the outliers, and it's usually not the people primarily targeted by the questions, either the very clever or the very weak ability students, and reflect something like miskeying, wrong key, or using a lot of guessing and other things that we will see. So problems at the infit area are more dangerous. Generally speaking, the overfit is it means that the set is more predictable, and it's not a major derangement from the Rasch model as much as the underfit. So the most dangerous is the underfit infit, and then the underfit outfit. So let's see Rasch misfit, which will go to overfit now first. The causes of the overfit is usually the redundancy, in which questions are repeated or nearly duplicate questions, very similar mirror items, or there is item dependency that one question will lead you to guess what the other question is. The correct answer of the other question. So it's easy. They are predictable set. If the set is predictable, it will cause overfit. Test lists also shared items. Items depended one on the other. Test wideness and queuing. If one make a lot of queues in the questions, they will be predictable. Repeated items over years. If you always use the same items, so people get to know them and memorize them. So also the set will become over predictable. Over coaching, like the institute will teach the students to the test, will tell them how to, pass the test specifically. So this will also cause the set of questions to be over predictable. And sometimes there is a restricted ability range. The cohort is very homogeneous, so you won't see a lot of underfitted. They will be all overfitting. And sometimes artifact in scoring also can remove noisy cases, like you take out the noisy cases and these things. It will lead to and this is iatrogenic, let's say. Uh, Also, if there are some questions that are too easy, too easy to answer, too easy questions also become very predictable with very weak distractors, so it's easily to predict the answer. Yes. And there are other things like content chaining and small samples. Small samples sometimes make the bins if they have a lot of uh, heavy binning. The bin have a lot of students in it. It appears to be like an overfit. So these also can be affected. So the overfit in the infit area usually is due to double items, redundant near duplicates, very similar mirror items, and item dependency and local, as we said. But the outfit overfit is usually due to repeated items over years. That's why people will know it. Even the low able students will know how to. There's repeated exposure on these things, so it will cause sometimes outfit overfit is not the outliers will do it better. Those students at the difficulty level of it might not be aware of these things. But however, both of them will share the queuing and the test wideness, over coaching and restricted ability range, and most of those. The Rasch misfit, which is the underfit. The underfit now is difficult. The underfit is not the set of questions is not over predictable. On the other hand, no, it's confusing. In underfit, there is confusion. Either the wording is confusion, the questions are not clear, or there is an extra dimension, as we said before, that like pure good language or very skillful language or high logicality testing other dimensions. So it will cause also underfit because it's not examining the trait alone, and people will differ on it. Also, distractors that are very poor and misleading, negatively discriminating items, linguistic problems, as we said, and construct irrelevant difficulty like long stem layout, poor images, poor print. Curriculum mismatch, unequal exposure. I mean, some students know that subject, other students don't know it. More than one possible correct answer, ambiguous question. Or diff, which is differential item function, which like prefer females to males, or some socioeconomic groups, or geographical location, or racial. Wrong key. Wrong key also can cause bad key. Guessing sometimes, low effort, carelessness. It's better to see how these things behave. Let's take outfit underfit. The outfit underfit, which is there at the peripheries. At the peripheries, what happens is that wrong key, bad key will make the good students have lower marks, and the bad student might have higher marks because the key is wrong. So it will cause outfit. I mean, it's not the expected. It will cause a lot of noise because that's unexpected. Because outfit, it means that there is a lot of noise, a lot of unexpected things. This is what it means, that the outfit is outfitting. Also, guessing will cause the lower student to have higher marks sometimes. Low effort or rapid responses and carelessness from high students can do that. Slips, sometimes speediness, time pressure effects also can cause high ability students to appear low. Or hasty bubbling, when they shade the bubble, they shade it in a bad way that the OMR machine will read it wrongly and will cause OMR scanning errors, or it will also, during the bubbling, he will bubble the wrong answer. Sometimes poor data entry. Sometimes problem happens with data entry and coding error. This is iatrogenic, not due to the students. And of course, cheating. When you see low students, a lot of them having good marks, so this might make you think of collusion and copying. Copying mean taking responses from another student, right? Correct responses from another student. Now this is the outfit underfit, but the infit underfit is the worst. This means that the question itself is bad. Look, confusing, unclear question, multidimensionality, dysfunctional distractors, negatively discriminating item, linguistic problem, construct irrelevant difficulty, curriculum mismatch, unequal exposure, more than one possible answer. So these are very harmful. Diff, which is differential item functioning by group, like gender or socioeconomic status, will affect both actually, the outfit and the infit. So this is important to consider when one see the infit and the outfit. Now this is one of the nicest thing here is what we call the right map. In the right map, on the left, you see these are the students. These are the number of the students. This is student number 69. This is student number 49. So this is the abilities. This is the logit scale. And the logit scale is a common scale for both difficulty and ability. So those people, for example, here, they are near the zero point 0.5 logit ability. And these questions are also questions that have difficulty of zero point 0.5 logit. So these questions are meant for those people, are targeting these people. So we see some questions have a circle on it. These are the anchor items. These are items that are shared between two tests. This actually is about two tests. This is the second test, exam two items. And these are the anchor items. They have the same number. So question number 33 is exactly the same as question number 33 there. It has the same number. And you see that they seem to be similar in distribution. But when we come and equate both, that's the nice thing, that we can equate them on a common ruler, as we said before. Equate exam 2 and 2, and you will see that. Oh, sorry. Let's do the equation now. Look, now. Now this is nice. Now you see the anchor group is equated. Question number 33 is 30, 37, 33 is 33 here. So they are equated exactly. They are giving exactly the same difficulty. Same questions will have the same difficulty. And we will drag all the others with them. And you will see that what happened. What happened is that these become lower. So this is what we call a common ruler. It's not just a common ruler between ability and a common ruler between difficulty. No, it's even horizontally. You have a common ruler between difficulty and ability like that. So it's horizontally and vertically. That's the beauty of the Rasch model and the equating that it can do. So what happened is, if one wants the details of this equation, let's take some anchor question and see where it is. For example, question 1 in this set is at level 0, 0 logit level of difficulty. Now we go and see question 1 in this set where it is in exam 2. Is it at level 0? Let's see where is question 1. Try to find it. Here is question 1 at level 1. So it is higher one level. This happens due to the calibration problem. The calibration problem, it says that the zero logit or the places of the logits are not the same. So you need to equate them between different, tests. So zero is at the one, sorry, question number 1 is at 1, while there it was at 0. This means that this set is higher, is at a higher location. All of these, the abilities and the difficulties, all of them are one level higher than the other. Okay, so if we consider the blue question is the real question in our item bank, so we need to bring these lower by 1 unit, all of them lower by 1 unit. Now this appears to be, so it appears to be this set of questions appear to be similar to the other, but in reality, the whole question, the whole set is one logit higher. So this is artificial. This is only, this is not true. So when we equate them, if we consider that the blue question is the real one in our item bank, so we need to bring all of those down, all of these down. So let's equate and we'll see how it compares to the first one. This is the first one, our question in the item bank, and we'll see how the difficulties will and the abilities will compare across both sets. So equate exam 2, look, that what is happening. The anchor item are equated well. So 7 is with 7, 17 with 17. So they are equated, they became the same level of difficulty because they are the same item. So they must be equated in the same difficulty. But look what happened to the ability. All of them went down. Those were showing all to be up, but in reality, that's their real ability in comparison to those. So the red question students are less able than the blue question. Students. So that's the nice thing about equation. We put them on a common ruler, both horizontally and vertically. Ability student on the common ruler, and also the difficulty of questions are under a common ruler. So this makes them more objective because they are comparable outside the exam. If the other exams also they are Rasch fit. So that concludes this session. So we now go to another thing. We saw in the other one that there are anchor. There's these anchor ones. These are the repeated questions. We call them the anchor questions. So what qualities? What are the characteristics of a valid anchor questions? When we choose anchor questions, which are questions repeatable between tests, across tests, we need to be careful because it's those questions. They are the one which we will depend on equating uh, our abilities and our difficulty items with. They are the pivot of equation. They are what they determine the equating process. So they must function equally across groups. There's no differential item functioning, no gender advantage, no socioeconomic advantage, no language advantage. Across groups, I mean, these groups, the gender, socioeconomic, language advantage, difficulty remain identical after controlling for ability. So this is important, right? Uh, so these are very important that shouldn't be, they prefer some people to other people, because if the other question, the other exam had, for example, more females in it, and these anchor items showed differences, we will lose the equation. We cannot equate them because they will affect on the equating process. Also, there should be no item drift. Item drift mean the change of difficulty of item across time. Difficulty must remain stable across semesters and years. This means that you shouldn't put anchor questions, those that are known to be repeated a lot, because I mean from prior exams, because they will be easier because they are repeated, so they will be easier. The difficulty will be less. And also, you don't put anchor questions that you know that there will have different emphasis on them over years. Like, for example, a year came with COVID, and then we have a lot of examination or exam items about COVID and something like that. These are clearly subjective to be different in time. Or you think that there are items that there will be coaching on them and teaching emphasis on them that will change over time. So you pretty much you should choose items that are stable in difficulty over time. So the most important thing is that there should be no diff, which means that difficulty remains identical after controlling for ability. It means the same groups, for example, this female or males or socioeconomic, they should have the same difficulty as long as they have the same ability. So there is no differential item functioning, and the difficulty must remain stable across semesters and years if you want to have no item drift. Otherwise, this will be wrong because the item will drift in difficulty, and you lose the anchor, your anchor, because there will be changes that are not merely differences in the location of the points that happens due to the way how Rasch is calculated, which cause them to have difference in calibration, and they need to account for them. That's what the anchor group do. They serve to relocate them in the right way. But if there are differences more due to more dangerous reasons like diff or drift, so our anchor won't function. You will see that you cannot have these anchor all the anchor item differing from each other across questions by a simple fixed additive value that you can calibrate on, like how we saw that all of these anchor questions from the prior exam are differing by a fixed value. Let me show you what I mean. In the prior one, when we said exam number, look at exam number one, although this might be a different one showing now. Now, this is a different set of questions. Now, let's say exam number 23 is on 0. Let's see where is exam number 23 here. It should be possibly on 1. Let's see. Yes, it's on 1. Let's take another exam. Let's take another item, I mean. Let's take the item number 22. Here it's on 1. So possibly there it will be on 2, because the other set, you will see what is the item was item number 22. Okay, let's see where is item number 22. It will be on 2. So all of these items will differ by one. But if you have these items showing different functioning for females and males, and they won't differ by one, they won't differ by one factor. So you cannot equate them, because here after we equated them, all these item, all these items after equating them became one. And look at the items here. Number 23 is here. Number 23, number 6. You should see number 6 also here. Where is this? Is number 6? Yes. Number 26. This is number 26. So you'll see them equated on the same level because they are the same questions. They should have the same, difficulty level. But if there is diff and drift, you won't see that. You will lose this, and so you cannot equate questions. So it's important that the anchor group shouldn't show diff and drift. No diff, no drift. So one should be careful in choosing which question should repeat across exams. Now we come to the last of the various concepts we want to examine here, which is the same concept of fitness, of fitting. And here we will speak about descriptive versus prescriptive modeling. Many psychometricians or psychometrists consider the Rasch actually to be not belonging to the item response theory. They differentiate between the Rasch and the other models like the 2-parameter logistic and the 3-parameter logistic. The main reason because the 2-parameter logistic and 3-parameter logistic and item response theory in general, even sometimes the first parameter logistic, which is the Rasch, sometimes are only used for descriptive purposes. While mainly the Rasch school, use the Rasch, only the Rasch, as a prescriptive model. Now there is a difference. There is a great difference between descriptive modeling and prescriptive modeling. In descriptive modeling, I always want to put an analogy so that one can understand that very well. Let's say that you have a person and you want to make a suit for him. Now, descriptive modeling is similar to saying that the tailor will change the suit to match each body. So different bodies will have different tailoring. And so what happens is that you will go and you will see the dimensions of the body of the man, and you will make a suit that is similar to him. So you do that, you do this tailor just suit, you will cut it, you will calibrate it, you see how it fits to him. So a suit that doesn't fit, you want to give it to him, you will fit him to the best suit. So the model should fit the data here. That's what we say. The model is fitting the data. The suit is supposed to be the model. The person is supposed to be the data or the items. So since our exam is composed of item, which is here represented by the person, the model, which is the 3-parameter model logistics, which is supposed to fit the responses to these questions. So the best fit is a descriptive manner. We need to see which model best fit the questions, best describe the responses of the students. So here, as a descriptive method, Rasch might not fare very well because Rasch assumes a fixed discrimination, which is number 1 mostly, and the guessing is 0. But that might not be true. An item might have a lot of guessing and might not be discriminating at 1. So the Rasch model might not be the best fit descriptive wise for that item. So descriptively, Rasch might not be the nearest fit to him. Okay, it's like Rasch is something else. The Rasch model is prescriptive most of the time. What we mean by prescriptive is like here, when there is a party and they tell people that they should wear, for example, a certain style suit whose size is, let's say, maximum size is large, or the certain size suits that should come from this shop, and this shop only have these type of suits which is maximally of size large. So if a man come and his size is X large or 2 or 3X large, then actually the nearest suit to him is the large suit, yes. But that suit won't fit, although it is the nearest suit to him, but it won't fit him because he is bigger than that suit. So pretty much similar thing happens when there is a failure of Rasch fitness. Although the software is computing a Rasch model that is near to you, the nearest to you, but that doesn't mean that it will fit you because it's the nearest to you. It's like here, it's like a suit which is nearest to you, like it's large, is the nearest to XX large. It's nearer than small, nearer than medium to XX large, but still doesn't fit. Or sometimes when it fits overfitting or something like that. So this is an analogy to understand what we mean by fitness, descriptive. The descriptive models uh, will change the model in order to fit the description of the data. Okay, it will relax the model, will change the model parameters in order to fit the description of the data. That's why you have two parameter logistic, three parameter logistic. It provides a better description, a better descriptive model. But the Rasch model is not descriptive. The Rasch model is prescriptive. It tells us of a model that the data should fit into, that the data is ought to fit into. Even though the Rasch model might not be the nearest descriptive model to it, but it describes an ideal that the data must fit into and must, uh, abide by it. And if the data doesn't fit to it, then we will change some of the data. Actually, it's not we will sacrifice the model for the data as in the descriptive case. No, we will sacrifice the data for the model. We will change or revise some items or even delete some items of the exam in order to make it fit the Rasch model, even though that is not the best pattern model, but it is the nearest ideal model that is useful for standardization of exams to it. So for a descriptive model, for example, in the descriptive modeling like two parameter and three parameter logistics, it's a flexible model that adapts to observed data pattern. So the model adapts to the data by adding parameters, different discriminator, guessing, of course, difficulty. The goal is to represent observed item behavior as accurately as possible. So it's descriptive. Misfit often leads to model expansion. يعني ده if that data doesn't fit this two parameter model مو مشكلة يسوي 3 parameter model وشوف إذا أكو 3 parameter model that will fit it. So I will sacrifice the two parameter model. I will go to the 3 parameter model. Not necessarily item removal. يعني I won't remove the items. No, I will change the model in order to better fit the items, in order to have a good description of the items. Emphasis is best fitting explanation of what happened in the test. So the item response theory, which is what we mean two parameter and three parameter logistics, is often have a descriptive philosophy. The problem with that is although that it describes the model and the item behavior very well, although the models, these two parameter and three parameter logistics, they are better descriptive. They provide better description of the behavior of the student responses on the items in the exam. But still, that information is model dependent. Model dependent, and there is a great variability between these two parameter model and three parameter models. This family is quite diverse. It's not like the Rasch model, which only differs by difficulty. They differ by discrimination, they differ by guessing, they have a lot of differences. So you cannot generalize the results beyond the model. Or if you do it, you do it with a very great difficulty. This is unlike the Rasch model, which is prescriptive. In a Rasch model, there is a fixed measurement rule, which is the model that defines the standard. So we fit the test to the model. While in descriptive, what we do in descriptive, look, in the descriptive, we fit the model to the test. While in the prescriptive, we fit the test to the model because we want our test to be as much as possible near to the standard of golden measurement. So what we do, the measurement rule, which is the model, the Rasch model, is fixed. We fix the discrimination, we fix the guessing, we already change the difficulty. Items should behave within variance. It means equal discrimination in Rasch form. There is no differences in discrimination. Goal, create a ruler-like scale where comparisons are stable across items and groups. The ruler that we spoke about in the first slides. Misfit leads to test improvement. يعني misfit, if there is misfit with the Rasch model, no, we will revise the test itself, not the model. We keep the model, but we fit the test to the model. We edit, replace, or remove items, or address differential item function and manage testlets. We do these. We don't change the model. We keep the model fixed. We change the item to suit that model. Sorry. And at last, the emphasis best fitting explanation of what happened in the test. No, this is the descriptive, sorry. Take the prescriptive. Next. Emphasis here in the prescriptive on meeting a measurement standard, not maximizing fit by adding parameters, by relaxing the model. No, we need we need the test to meet the measurement standard, which is the Rasch standard, which is the best standard. Although not always is the best standard, sometimes it's not. So from that we conclude that we should, have efforts to make our model as much as possible meet that standard of fitting to the Rasch model, so it can become more objective and the items can be compared to other tests if they reach the Rasch model also. So this will be good for item banking and it will be good for achieving justice with the students because it will compare between their abilities. And this is what all the test is about. It's about the abilities of student. So the ability of student shouldn't be their final mark as it is present in classical test theory. No, it should be the ability assigned to it by a Rasch model if it fits the Rasch model. And that is more objective and most comparable across much comparable and more objective and more comparable across tests than the classical test theory criterion, which only works within the same exam. It cannot work across exams. So that's all for item response theory. I hope it's been good. Goodbye.